Hello, Sparse workshop attendees. I'm Emilien Bauer, PhD student here in Edinburgh. I couldn't come physically, but I'm still super glad to be able to present you this project in collaboration with Mari Gorbeni and Amir Shika from the University of Edinburgh and Tobias Grosser from the University of Cambridge. This project is all about compiling and compressing structured tensors. The way we see it, the tensor computational world right now is split between two extremes. On one hand, we have the structure-aware sparse tensor frameworks, which are able to co-iterate over only the values we care about and store only those values uh, to scale like nothing else, but are paying the cost of complex runtime data structures and the associated overhead. On the other extreme, we have those dense tensor frameworks, which assume nothing on the tensors, only compute every single element. But this way are able to get the last grip of performance of most hardware platforms. The way we see it, it's due time to fill the gap. So I'm here to introduce you two steps we took towards this goal. Former one, Struct Tensor, published in Uppsala in 2023, tries to reproduce those higher level benefits, structure-aware algorithms. And the second one, that's like just recently published in Uppsala 2025, is tackling a specialized code generation problem and data layouts to hopefully reproduce this lower level code performance benefits. So the talk will be structured with those two projects in mind. Let's first look at the concrete benefits we want to get from both worlds, right? So again, on the dense world, we have concretely great cache locality. The memory hierarchy behavior is great. We usually get fantastic parallelization down to instruction level parallelization with vectorization on CPUs, for example. On the sparse side, what we would like to reproduce is the storage benefits, being able to not store the whole tensor. And we want the complexity and scalability benefits, that is the compute cost side of things. We hope to bring all of those together in symbolic structure because there's no free lunch, right? So we have to restrict it somehow. This symbolic structure is the way we try this. So let's have a look at what we mean by this. The first step is the sparsity structure encoding. So we look at a diagonal matrix here and we want an encoding at compile time of this knowledge. We represent this with a set definition on the indices we care about. We see like simple bounds of x and y here and an equality of x, y, telling us we only care about those values that are on the diagonal. This is what we call the unique set in this context. Struct tensor works with this information and moves to structure inference, that is propagating this information across the programs, across the defined operations we're considering. For example, inferring the output structure of the product of two diagonal matrices. So we take those structures an input and we can simply guess that the output will be a diagonal matrix again. And we can do that in general for all those structures we include. Now, seeing that, we realize we can do more than just this sparsity reasoning. We can work with redundancy in that context. And so let's see how we encode that with a simple symmetric matrix here. You can notice we have two sets of indices now. We have the same bounds as before. And more importantly, we have here a transpose-like expression of those indices. This is to signify that we know those transpose element will hold the same value at runtime, whichever the value. And this transposes the definition of the matrix symmetry, right? From that information, what we can infer is a smaller set of the values we do need to compute, because we know that if we want to recover one of those lower values, we can get it from above. So we get this per diagonal subset in this example, which gets expressed as a unique set, which can get further propagated to look for further benefits anywhere else in the program. To clarify, this is not limited to noun structures as diagonals and symmetries. It's just those basic examples to show you this encoding, but it can work with pretty complex structures, as this one arising from the covariance matrix showing up in polynomial regression degree 2 as an example. But you can observe that it's starting to get more complex, and this framework is able to completely reason about that and leverage it to see the kind of results we get over that. Simply inferring this structure and generating code iterating over this subset of elements we do want to compute, we observed already orders of magnitude of speedups. So we get this complexity objective we wanted. We get scalability too. We can see the benefits keep scaling with the size of the problem because the sparsity keeps increasing, just like with this code iteration in the sparse frameworks. So we're super happy about those initial results. But at this point, we look at what remains, right? So this is the example of a code that struct tensor could generate for a diagonal matrix product. It achieves, again, this complexity scalability goals by generating one single loop that is iterating over this output unit set here and simply doing those computation on the necessary subset. Now, if we look at this instruction side for now, we can see that this still works with the old full matrix encoding here. We actually get elements of multidimensional arrays. So we don't get any storage benefits. The cache locality is completely is so bad because every time you will need to load the full line, yeah. It's pretty awful for the vectorization too. We get those huge strides between H elements despite their simple structure, and struct tensor did not deal with parallelization of the kernel so far. So here are the remaining goals. We start looking at the storage, first of all. And we think we have a pretty geometric representation of our sets already. One great formalism to work with those representations is the polyhedral analysis framework. It simply asks us to have only a wide generalization of affine expressions in our encodings, which we found to be no bother in all the studied cases. In return, we get the capacity to simply compute a linear index for each of those elements, which would be a great solution, right? We now have a function that returns us one unique index for each element of this subset rather than the whole matrix, which is just what we need to index them in a very efficient contiguous buffer containing only those values and none of the upper triangular we don't use here in this example. The polyhedral framework also contains utilities to generate those loops, just like struct tensor did with advanced branches, which is great. Yeah. So with this indexing, we can now simply plug this indexed compressed buffer in the computation. We know we're only iterating over those indexed elements. So it's as simple as putting it here. What it gives us is the storage benefits. We can now work with this simple diagonal only layout of those elements. Of course, it helps with the cache locality. There's no zeros to load and store in those caches anymore, and the vectorization is only improved because those elements are fully contiguous now. Now, this indexing even provides a degree of freedom in the order in which you define those elements. So the stack does use that to index them whenever possible in the very order we iterate over it to completely maximize this vectorization. This compression on top of the previous structure inference benefits stacks up from like five speedups on the very same problem. So this is only embedding this compression on top of the previous iteration style. On top of that, as mentioned, the polyhedral model can generate loops for us. So it's pretty mature and able to generate parallel loops too pretty easily for those restricted computations. So we used a very naive first draft way of parallelizing those computations. As in, it's not very specialized on that part yet, but we observe already a capability to scale pretty much as good as the best competitors on that criteria we had, which was PyTorch on this occasion. So we celebrate, we checked all our boxes. We get all the benefits from the sparse world, from the dense world, on those cases where we have those elegant knowledge to leverage, and all is good. So what's left for us to look at? That's where I want to go now. Concretely, struct tensor, then forwarding to DASTAC, does demonstrate the huge potential of this way to compile those problems, but it does so with a very specific DSLs, just carrying this computation we're looking at and those general noun structures. So it was great to experiment and demonstrate all that, but I do think it will limit any kind of real world impact this might have the potential of. So a first thing we want to look deeper in is more general structured computations, more general than simply addition and multiplication based tensor contractions. Here's an example from the AI world where they do use in attention layers the softmax functions, which ultimately boils down to summing exponents of elements of those tensors, here I as the input, to encode some relationships between those informations. They very commonly use very structured masks. Those masks are specialized to this exponential, such as you just add a simple mask to your input as a way to enforce some ignored element in the exponential. That is, this mask is based on zeros and minus infinities, so that the minus infinities in this case do collapse to minus infinity when added to the input, getting zero on the output, and the zero leave the output unchanged in this case. So we do feel like this could be reasoned in very similar terms with, right? It's just the formalism wasn't done this way so far, so I'd like to explore that to be able to use it in all those cases. More generally, I think the DSL approach is a limitation for the impact because the way I see it, structure is not a domain at all. It just naturally emerges in so many domains. So I do believe that what we want in some infrastructure in such ways that different domains, for example, probabilistic programming exposes a lot of structure in its discrete probability distributions. All of those, yeah, quantum simulation can be translated pretty easily to just combination of gates represented as small but very structured matrices, perfect candidate for this optimization framework. So they all have their different DSLs and specific optimizations already. But what I think such an infrastructure could help with is then translate them to this common representation and allowing even further co-optimization of those kernels beyond so widely different initial formalisms. So I'm pretty excited about that. And then it lets us imagine co-optimization between any kind of specific domains displaying such structures. There is initial work already on recovering structure from static, that is compile time noun tensors. It's a hard problem, but we're interested in exploring how this could potentially help co-optimization with those fields. And yeah, those static tensors are widely present in AI at the inference stage where the model is trained. And those weights are just huge tensors that we statically know. So we could have a lot of time to reconstruct this structure. Finally, I don't think structured tensors are the silver bullet, right? We will need sparse layouts for a while. So I do think it's necessary to think about interoperability. I don't want those two point of views to compete against the users. I want them to collaborate to give the best benefits to everybody. And that could be a great fallback for those complicated tensors. Finally, if we want concrete application, of course, we want more serious targets. Right now, this is heavily experimented on top of CPUs, and we do want to leverage those GPUs or distributed memory systems to bring it down. So here are a few of the leads we are planning to explore as much as we can in the following years. Here are the title of the two mentioned articles for those who would like to read more. My email address, feel free to drop me a mail and I'll be available as much as possible on the PLDI Discord. Thank you so much. Enjoy the rest of the workshop and hopefully see you soon.